Hello, this is Mr. Ferguson, and we're going to expand lesson 6.5, where we're talking about Lewis structures with an additional bonus section. We're going to talk about formal charge and resonance in this lesson. So we'd like to teach you to draw the resonance structures for molecules and to recognize what we mean when we say a resonance structure, and also to use the concept of formal charge to determine which Lewis structure is most stable for a molecule, or if there's multiple Lewis structures, which one is the more common or more likely form. So let's get to it. So what exactly is formal charge? Well, it's a method for determining the best distribution of the electrons in a Lewis structure. And if you go on in your study of chemistry to more advanced topics, you use the formal charge a lot to help you figure out the reactivity of molecules and what's going to happen in chemical bonding with molecules using the formal charge. But in simplest terms, the formal charge is going to be, this is formal charge, the number of valence electrons in an atom minus the unbonded electrons attached to that atom, lone pairs. So you're going to minus off all of the electrons in lone pairs, and then you're going to subtract off half of the bonded electrons, and you're going to do this for each atom in the structure and write a tiny little number beside that atom to represent its formal charge. Okay, so let's do this for two different molecules, carbon dioxide and then sulfur dioxide. So carbon dioxide, we know that carbon is a central atom. It's going to have an oxygen on either side of it. Okay, and we could draw this. We've done this enough times. We know that each carbon is double bonded to each of the oxygens, and each oxygen also keeps two lone pairs. So what would be the formal charge on each one? Well, let's do the carbon first. So carbon has, start with the number of valence electrons, 4 valence electrons. We're going to minus off any unbonded ones. Well, there aren't any unbonded electrons. There are no lone pairs on carbon. Okay, minus half of the electrons involved in bonds. So let's look. 2 electrons, 4, 6, 8. So there's 8 electrons attached to that carbon through bonds. Half of 8 would be 4, so it's 4 minus 0 minus 4, that equals 0. So carbon's formal charge is 0. Now let's do each oxygen. Okay, they're both laid out the same, so we can just do one of them. So oxygen has 6 valence electrons. We're going to subtract off the unbonded ones. There are 1, 2, 3, 4 unbonded. 6 minus 4 minus half of the bonding electrons. So we have 2, 4 bonding electrons. Half of that would be 2. 6 minus 4 minus 2 equals 0. So each oxygen is also going to have 0 formal charge. Alright, now let's try sulfur dioxide. Sulfur is our central atom. Oxygen on either side. Okay, and in this case, sulfur has 6 valence electrons. Each oxygen has 6. So that means we have 18 electrons to work with. Okay, so in sulfur dioxide, we're going to start by putting a pair of electrons between sulfur and each oxygen. We're going to complete the octets of each oxygen, and let's see if we've used them all. 2, 4, 6, 8, 10, 12, 14, 16. We're 2 electrons short, so we're going to put 2 more valence electrons on the sulfur, so sulfur would have a lone pair there. Now the issue is with this one, we can see, if we draw this like so, well, let's look at formal charge. Okay, sulfur, 6 minus 2 is 4, minus 2 more is 2. Sulfur has a plus 2 formal charge. 6 valence electrons minus the 2 unbonded electrons minus half of the electrons involved in the bond, which would be 2, so we still have a plus 2. Alright, let's do oxygen. 6 minus 6, because there's 6 unbonded electrons, minus 1. 6 minus 6 minus 1, that gives us negative 1. So each oxygen is negative 1. So that adds up to 0, so sulfur dioxide we can expect to have a 0 charge. However, and we didn't really cover this yet, that's on the next slide, the rule is you want to minimize the formal charge. So, and you can also see we have an issue, sulfur does not have an octet. That's a single bond, not a, looks like a double bond. So let's redraw that. Okay, I'll switch to black, so we're going to bring in a pair of electrons here like this. So now we're going to have sulfur double bonded to oxygen. Only 2 lone pairs left, single bonded over here to oxygen, and this oxygen will have 3 lone pairs. Okay, so now if we do, oxygen is going to come up with a formal charge of 0. This oxygen has a minus 1. Let's check sulfur. 6 minus sulfur had a lone pair, sorry. 6 minus 2, okay, that gives us 4 minus 3 plus 1. Alright, so we've done a bit, we've got one of the, and this structure would be more stable than this one because one of the atoms has a 0 formal charge. But I think you can see sulfur has 2, 4, 6, 8 electrons. Okay, so this would allow us to predict that this would be a more likely structure than this. And again, as we're going to see, sulfur can actually expand its octet, and so it's allowed to actually have more than 8 electrons in it in order to minimize formal charge, and we'll talk about that on the next slide. So, how do you know which one's the best Lewis structure? The best Lewis structure is first of all going to have the octet rule satisfied for all the atoms. There are some exceptions, okay? And it's going to have the lowest possible formal charge on as many atoms as possible in the structure. So if we remember with sulfur dioxide, we had it drawn, this way with a single bond to each oxygen and a lone pair there. And this resulted in a minus 1, a minus 1, and I believe that was a plus 2. And then what we'll do is we show like this could also be, this structure, single bond here, and lone pair there, and that gave us a minus 1, a 0, and a plus 1 and a 0. So that was from the previous slide. Well, using the same reasoning, why can't we bring in another pair here? And so we could have our sulfur central, okay, and lone pair. And I know what you're probably thinking, well, we have an octet rule violation right here. Let's go ahead and figure out the formal charges anyway. We'll come back to that octet rule violation. So that each oxygen is going to have a 0 formal charge. How do I know that? 6 minus 4 unbonded electrons, 1, 2, 3, 4, minus 2, that would be half the number of the electrons that are involved in that shared bond with the sulfur. That's 0. Same thing for this one over here, 0. So let's move on to the sulfur. Sulfur had 6 valence electrons as well, minus 2 unbonded, and it's got 4 total bonds. 4 bonds, 1, 2, 3, 4. So that's 8 electrons. Half of 8 is 4. 6 minus 2 minus 4. That's 0. So this one we can see we've minimized the formal charge. That is an even better Lewis structure than either of the first two. So we would predict that this is the likely arrangement of the electrons. Now, The problem is sulfur has 2, 4, 6, 8, 10 electrons. You're absolutely correct. That's called an octet rule exception. We're going to deal with that on our next slide. So we do have some octet rule exceptions, and we've already covered one of them, and that's that duet rule, where tiny atoms like hydrogen are stable with only a single pair of electrons in their electron cloud. But let's go up to the other end. If we have central atoms that are in n equal 3 or more, in other words, that would be the third row of the periodic table, they are actually, we find that they will expand their octet in situations where it serves to minimize the formal charge, that is to bring the formal charge of more atoms in the molecule to 0. So let's look at, I have 4 different arrangements for the atoms in an SO3 that would be sulfur trioxide. So here we can have 3 single bonds to the sulfur, 1 oxygen double bonded, 2 single bonds, 2 of the oxygens double bonded, and 1 single bond, or all 3 of them double bonded. And of course, using the octet rule, only this middle sulfur, only that one and the second one would actually have an octet on the central atom. But I think if you count them, you're going to find that they all have 24 electrons in them. So it's kind of 4 different arrangements with the 24. Now if we went and did the formal charge and took a look at the formal charge here, we would find that these oxygens all have a -1 when they're single bonded. So that's 6 valence electrons minus 6 unpaired electrons minus 1 of the bonding electrons. That adds up to -1. Okay, our central sulfur's formal charge is going to be 6 minus 0 unpaired minus 3. So that's going to be a +3. And of course, +3 and the 3, it adds up to 0. So, and since this is an uncharged molecule, it should add up to 0. Let's look at the second one. Well, now we're going to have a -1, a -1. The oxygen, when it's double bonded, has a formal charge of 0. 6 minus 4 minus 2 is 0. Let's look at the sulfur in the center. 6 minus 0 minus 4, that adds up to +2. So again, +2, -1, -1, net charge 0. So we're better because we have a lower formal charge here than we, so the formal charge on the sulfur here is lower than here, and we have actually one of the atoms with 0 formal charge. Let's look at the third instance. Okay, we have a -1, 0, 0. Now sulfur is going to be 6 minus 0 minus 5, which adds up to +1. +1, -1, 0. So this is an even more likely configuration. And the third one, or the fourth one, excuse me, we have 0 formal charges on all the oxygens, and it's actually going to be 6 minus 0 minus 6, which is 0. So this, you would think, would be, from a formal charge standpoint, the most likely distribution of electrons, even though the sulfur has taken on an extended octet. It actually has 12 electrons. It's formed 3 double bonds, and but you would find that this is probably the most likely arrangement for the electrons because sulfur is in the third row, so it's allowed to expand its octet. So one final point we want to discuss are resonance structures. You can sometimes have multiple valid Lewis structures for a molecule, and we call them resonance structures when these different structures or molecules arrangements are differing only in the position of the electrons. So we've got a sulfate ion here, SO4 minus 2. And you can see we've drawn it with all single bonds in the first instance, which gives you, formal charge of -1 on all of the oxygens, and then a formal charge of +2 on the sulfur. The second one, we have a double bond between the oxygen and the sulfur, one of the oxygens and the sulfur, the rest are single bonds. So now we notice we've reduced the formal charge to +1 on the sulfur, and then only 3 of the 4 oxygens have a -1. This one would be a 0. So this would be a better structure. And then we get to the third example. We have double bonds on the opposite sides, and single bonds to these oxygens, so the oxygens top and bottom. So we have formal charge of -1 here. Everybody else has a 0 formal charge. Note that sulfur has expanded its octet again, which is okay. But this serves to minimize the formal charge even more. So out of these 3, definitely this one is going to be the preferred and probably the more likely distribution of electrons. Okay, but if you think about this now, so let's say this is how it's going to be. We've kept the octet rule for sulfur, for the oxygens. What would be a resonance structure we could draw? Well, we could draw sulfur with the double bond up to this oxygen and a double bond down to this oxygen, and single bonds over here to this oxygen, single bonds over here to this oxygen, and the overall thing is going to be a net -2 charge, because again now these 2 oxygens have -1 formal charges each. So basically, is it this one or is it this one? And the answer seems to be that it's both. That's a stable arrangement, so it's likely to be in either one of those arrangements. So we will draw it as kind of arrows, like this seems to go back and forth between these two. And when they actually look at the bond length, what they find is that between any sulfur and a given oxygen, the length of this bond seems to be longer than a double bond but shorter than a single bond. So it's kind of like all 4 of those are midway between a double bond and a single bond in length. So that's what we call resonance. So those are equivalent structures, just we've distributed the electrons slightly differently in each one. All right, so I know this is some kind of advanced stuff, but it is helpful if you understand the idea of formal charges in dealing with these Lewis structures and kind of figuring out which one's most likely. Are they resonance structures? So there are 4 resonance structures shown below for the phosphate ions. And I need to move something here, excuse me, I need to move this. There's actually 5 resonance structures, excuse me. And actually 4 of them are resonance, and then 1 is just an alternate distribution. So you're going to have to figure out which one is the most likely structure or structures out of the 5 based on formal charge. So what I'd like you to do is draw them and then figure out the formal charge on each atom in each diagram. And of course, if you're looking carefully, you're going to note that this one, this one, this one, and this one are really the same thing, just kind of turn the double bonds in a different position. So you really only have to do the formal charge of this one and this one. And then these will follow suit off of that. So remember that formal charge is going to be valence electrons minus the unbonded electrons that are attached to that atom, that says unbonded, minus 1/2 of the bonded electrons, since half of those could be considered to belong to that atom. So give that a try. See if you can figure out the formal charges and which would be the most likely structure. We'll talk about it tomorrow.